Okay, we wish to conclude Chapter 10, the last half of Chapter 10, by discussing H-R diagrams, Hertzsprung-Russell diagrams. These diagrams are a method to classify stars so that we can understand them better. Developed by H-R Hertzsprung and Henry Russell, hence the name. On the vertical axis we have absolute magnitude, which, as we discussed in the last lecture, happens to do with the absolute luminosity of the star itself. So the absolute magnitude is the standard luminosity of the star. And on the diagram it increases from the bottom to the top on the vertical axis. The horizontal axis is temperature, which is also the spectral class of the stars. And that increases from right to left. So you have the hottest temperature right at the origin of the diagram. And then as you go towards the right, you get to cooler temperatures. And the spectral class will progress in that manner as well. So here's a look at a H-R diagram. Absolute magnitude and luminosity on this vertical axis over here, going to a higher magnitude or a more negative, so greater luminosity, brightness, as we go up on this axis over here. And highest temperature over here on the left, going down in temperature as we go to the right. And also designated by spectral class here. Well, what is spectral class? There's a certain way to identify spectra, and it happens to be associated with the temperature of the star. We would note that in most stars there's hydrogen. In the majority of stars it's hydrogen, unless it's a dying star and it's burned it all out. There's basically hydrogen, and in some stars the pattern of hydrogen would be more prevalent than in other stars. Generally, it might mean that there's more hydrogen present, but not all the way, because at some point, if the star becomes too hot, then the hydrogen will get ionized, and you won't be able to see the signature of the hydrogen as well. So the hottest stars might not have the best signature of hydrogen. In fact, originally, the greatest signature of hydrogen was designated A, and that was just it was thought to be the greatest amount of hydrogen, but it basically just designated a certain temperature of the star. And so now the spectra that has the greatest signature of hydrogen is now spectral class A. As we actually get to the cooler stars, they actually might have more atoms, actually making even molecules and being able to absorb more energy in their molecular levels. Hence their spectra is more complicated, and they're cooler, so you might even have molecules of, say, titanium oxide in their spectrum. As you get really hot, the hottest stars, you're ionizing even the atoms so that they don't even have electrons, orbitals, and the very hottest stars would show a signature, a very easy signature of ionized helium in their spectrum. Those are classified O. So we would say that originally stars were classified according to their hydrogen line intensities, and those started out A, B, C, D, and so forth. But found out that this was actually not the best way to classify according to temperature. And later the letters were reshuffled in order of decreasing temperature. So as they were reshuffled, it turned out that O was actually the hottest, B was the second hottest, A, F, G, K, M in order, like that. So in terms of temperature, now you can use a mnemonic device, a memory device, to remember this order of hottest to lowest temperature, O, B, A, F, G, K, M, And the phrase is, "Oh, be a fine girl or guy, kiss me." And that helps remember OBAFGKM. So here is our HR diagram. Absolute magnitude or luminosity on the vertical axis, going to higher brightness, up to negative magnitude, and then higher temperature to lower temperature, also designated by spectral class, OBAFGKM. Oh, be a fine girl or guy, kiss me. Or my own mnemonic for you, memory device, is if one is being all frugal, go to Kmart. Works for me. The main sequence is a line that kind of finds its way across the diagonal from the upper left to the lower right, and 90% of all stars fall on the main sequence. They all have some characteristics in common, and the main characteristic is that they are relatively young stars fusing hydrogen into helium. So they are doing the basic hydrogen into helium fusion process, producing their energy that way. And that's what we say, that 90% of the stars out there are doing that, and they comprise what we call the main sequence. The Sun is sort of towards the center of this main sequence. There's the location of the Sun at 1 solar unit. We can actually go to greater mass, which would bring us higher on the main sequence, and lower mass, which would bring us, of course, down on the main sequence. With the Sun being near the center at 1 solar mass. On the main sequence, you can also determine temperature. The hot stars tend to be brighter, so as the main sequence goes up to greater absolute magnitude, which would be a minus magnitude actually, the hot stars would tend to be bright and hot on that scale. They would tend to be blue in color. The cool stars tend to be dim, so they'd be down near the lower right. And they would tend to be rather reddish in color. For example, Sirius is quite a bit hotter than our Sun. It's on the main sequence, and it is a Class A star, so it is hotter than our Sun, which happens to be a Class G star. Astronomers have found that the majority of stars are actually small and cool Class M stars, which are called red dwarfs. So the majority of stars in the sky are actually cooler than our Sun and are red dwarfs, not very bright. Example would be Proxima Centauri, the closest star to Earth other than the Sun. And our Sun is a Class G star, G for suitable for the general audience. It's a Class G star in the middle of the main sequence, and rather yellow color. So here's a HR diagram of some well-known stars, the main sequence designated by this black arrow that I just drew. Some of the best-known stars, you have the Sun here in the middle. Alpha Centauri, which is a very similar star to our Sun, is very close to the Sun on the main sequence. So it is a main sequence type star doing the same thing our Sun is, and just about the same luminosity, just a little bit brighter than our Sun. And so it's a very similar star to us. We have some brighter stars, Altair and Sirius A and Vega, which are on the main sequence here. Much brighter than our Sun, greater luminosity. Down here toward the lower right, we have some red dwarfs, which is Proxima Centauri and Barnard star. And they are very hard to see. Here's another look at the main sequence. We have these spectral types. Oh, be a fine girl, kiss me. The hottest temperature being around 25,000 K on the surface. our sun being around 6,000 K, and getting down to the red dwarfs, which might be around 3,000 K. We can further divide these spectral classes, these spectral types, into numbers from 0 to 9. So as we proceed from the left to the right, we would go from 0, O0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to B0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to A0, and so forth as we go from left to right. So the hottest would be, say, O0, and then we get cooler as we get to O9, and then the next coolest would be B0, and up to B9, and then A0, and so forth and so on as we proceed to the right. The lower the number, the hotter the star. So 0 is the hottest, and proceed to cooler down to 9. So the more exact spectral type for the sun itself is a G2 star. So we're not quite at G0, we're a little bit to the right at G2. Most of the stars near us that we might see in the sky, or that might actually be in the sky, are to the right on this main sequence, kind of towards the lower end here. Our star being a G2, kind of a yellowish star. Main sequence stars on the lower right are called red dwarfs, and actually most of the stars in the sky are red dwarfs. Now, you can't visually see them because they are below the visual range to be seen. But indeed, most of the stars out there are indeed red dwarfs, and you can't see them. They're below the visual range. You might be able to see them if you could see in the infrared. So there must be some animals like dogs, or especially the animals that hunt at night, cats. They can see in the infrared. They can see heat signatures of their prey, and hence if they were to look out into the sky, they would see a much different sky than what you and I see. They would see the sky that we see plus a whole bunch of extra stars, these red dwarfs that are hanging around in the infrared. So that might be pretty interesting if you could see like they could see. Red dwarfs are on the main sequence, so they're doing the same thing that our sun is doing. They're burning hydrogen into helium, but they're doing it more slowly. So they're going to last for trillions of years. They're going to last much longer than our sun because they are smaller and they're burning hydrogen into helium, but they're doing it very slowly. And so they're not as luminous as our sun, but they're also going to stay around for quite a while. As we go to the other corner of the H-R diagram on the main sequence, we would see most of the bright stars in the sky, the ones that you and I see quite clearly. And these are blue giants, very visible, very bright. And the reason we actually see them is because they are so bright. I mean, they could be very far away, but they're so bright that we see them in our sky. So the sky that we actually see might not be quite depicting the true sky that's out there nearest to us. The sky that we see are just the bright stars that happen to send their light to us, and those are mainly the blue giants. Blue giants are very hot, very luminous, and because they're very hot and luminous and main sequence stars, they are burning hydrogen into helium, but they're doing it very fast, and so they're going to burn themselves out much faster than, say, our own sun, and in fact, much faster, definitely, than the red dwarfs. So they're going to burn themselves out after a few million years and become older stars after that, while our sun is burning its fuel for another 5 billion years. So even though the blue giants are much bright and very luminous and easy to see, they won't be there quite as long as our own sun. If we go off the main sequence, we can find ourselves in the supergiants and giants. like Betelgeuse, they're quite luminous because they're so large and so they have so much volume and mass, but they're cooler, so they're not quite as hot, but they're luminous because of their size. And they're off the main sequence because at this point, mainly they're not fusing hydrogen into helium, they're fusing other elements into greater elements on the periodic table. So they're cool, but they're bright because of their enormous size, not because of their temperature. They may be about the size of Earth's orbit or even larger. As we go to the lower left, we'll see stars that are not so bright, not so luminous, but very hot. These could be white dwarfs that are under great pressure, and they're very hot, but very hard to see because they're just really small. In fact, they're on the size of Earth itself. As we look at the H-R diagram, we have the main sequence, and in fact a lot of the data that we have placed on this diagram comes from the European Space Agency Hipparcos satellite that has collected data of stars up to about 200 parsecs away from us, which includes about 1 million stars. So this data is collected, has 1 million stars on it, verifying that 90% of them are on this main sequence and the other 10% are off, either H stars that have ventured into the giant stage, or beyond that, exploding stars leaving a remnant of, say, white dwarfs. On this H-R diagram, there's another way to classify stars. We can note that the width of a spectral line is a measurement of a star's internal pressure, and that in turn can give us an idea of its luminosity and size. A red giant, because even though it's massive, it's so large that it doesn't have as much pressure on its plasma than, say, a main sequence star, which is much smaller but under greater pressure. And in fact, a white dwarf, which is really small, about the size of Earth, but under a lot of pressure. So this would be manifested in the width of the spectral line that you might see. So the luminosity class is another way to classify stars on their width of the spectral lines. And knowledge of the luminosity class would then allow astronomers to identify the object according to its size and luminosity, make an estimate of its luminosity, and hence, based on what kind of star it is and its luminosity, and what kind of star would give us an idea of its size, then estimate its distance based on that. So this is a way to use spectroscopy to estimate its distance, as we hinted at in the previous lecture when we said that we can use spectroscopic H-R diagram to estimate a distance to a star. Here are the luminosity classes. We have 1A, 1B, 2, 3, 4, and 5. 1A are the bright supergiants. We can go from blue to red. 1B are just the supergiants. 2 are the bright giants. 3 are the giants. 4 are the subgiants. And 5 are the main sequence stars, or dwarfs. So all the stars on the main sequence are luminosity class 5, including our Sun. So we have all these classes, 1A, 1B, 2, 3, 4, 5, basically designated by the pressure of the spectral lines, but determining these luminosity classes and hence determining the size of these stars as well. the full classification of our own sun then is G2 luminosity class 5, G2 5, or Roman numeral 5, V. About half of all stars are members of multiple star systems. Most multiple star systems are binary systems. And almost all we know of stellar masses is based on the observation of these binary systems, because we can use physics and Kepler's laws to figure out the masses of these objects. Kepler's third law can be used to calculate the mass of the system by observing the rotational period and the size of the binary orbit. On the H-R diagram, stars with more mass are reaching up along the vertical axis of the H-R diagram. So as we go to greater luminosity, we are also going to greater mass, especially on the main sequence. As we look at the main sequence, we have smaller masses and greater masses we extend across the main sequence. So the main sequence stars range from about 0.1 solar masses up to, which are K and M masses, the red dwarfs, up to about 20 solar masses as we get into the blue giants. O and B stars, very hot blue giants on the main sequence. The more massive a star, the more rapidly it exhausts its fuel on the main sequence, as we said, the blue giants, and the shorter its lifetime on the main sequence. And so we could say very young stars, all the young stars are young, but the blue giants are going to burn out faster than our sun, and in turn the red dwarfs are going to last a very long time. Most stars that we identify are smaller and dimmer than our sun. I mean, that we can identify through all means. The red dwarfs represent most stars, and they're lasting a very long time out there. You can't see them, but they're there. Binary stars. Two stars revolve around a common center of mass. At least half of all stars are actually binary stars, and there are three ways to identify binary stars. One is through a visual binary. A visual binary would be if we took an actual visual picture of the stars, and over the course of years kept on taking pictures of them and watched them actually visually revolve around their own common center of mass. So each star is viewed widely enough so that it actually can be separated visually from the other star. And we would observe this over many years. As we see in this diagram here, we're looking from a period of time from 1948 up to 1983 for one cycle of this revolution. So that's many years. What is that? 35 years for this visual binary cycle in this case. Another way to observe a binary star system is through a spectroscopic techniques. We could use the Doppler shift in this case. These are for stars that cannot necessarily be resolved visually because they're so close to each other as you see it visually. But if you look at the light, you can see that sometimes one brighter star is moving towards you, sometimes it's moving away from you. So as they are revolving, we can observe their spectrum, and the spectrum would shift spectroscopically either to the red or to the blue as it is revolving around the center of mass. So we identify the Doppler shift of the spectral lines, and this can be observed over days or even shorter periods depending on how fast this revolution is taking place. The third way we can observe a binary, possibly, and we'd have to be pretty lucky for this to occur, is if the binary system happens to be in our same line of sight, the plane of our line of sight, such that one star eclipses the other star. We call this an eclipsing binary. So as one star eclipses the other, we would observe a change in luminosity as one star becomes in front of the other, and vice versa. The other star comes in front of the second star. So, looking at eclipsing binary, we observed a change in intensity over time, and evaluating the intensity, we can come up with some kind of measurement of the relative size of these two stars. So the revolution period and the orbit will also help determine the mass of the binary system. So like a spectroscopic binary, an eclipsing binary could have periods of, say, only days. So you make this measurement over a period of days to make this calculation of the star sizes. That concludes the second lecture in Chapter 10 on the H-R diagrams and the classification of stars.